Are all these lectures like we can watch them online?
I am trying to see if I can get them set so that I can just post them up for you. That's the hope.
Just gotta hit properties there.
Okay.
Right click on display capture.
Oh, did I?
I'll just like right click on it and then properties. Down all the way, like down properties.
Oh, properties? Oh,
yeah.
Okay. Oh.
And then.
Now it looks like it's there.
Just hit OK, maybe.
Okay.
Just kind of can't.
Yeah.
There's just some jank in general, especially for like laptops.
Okay. So I want to talk about some of the information that's available to you. In week 1, I put all of the data sheets and things that you need for the first kind of half of this course to do with the ARM. And so that's where you should go to look at this. So I wanted to go over a few of them. And so the first was copied over in week 1's lab, so that you had reference to where to wire things up. Yeah.
I want to like CN and like pin diagram.
Yep.
Like for example, like 25 and 26. Like when I plug in on one side it works, the other side it doesn't. I assume they would be the same.
So if you say 25 and 26, so right here?
Yeah.
So are you saying plugging in here and here?
Yeah.
It's a weird way that they've drawn this, okay? However they've drawn that. These are 2 rows of our pins. So 2 is connected to PC8, 1 is connected to PC9.
Oh.
They are not connected together. They extend on the top and bottom of the header, so you can go underneath. And of course, they go straight through. But here it looks like all 3 of those are connected, and that is not true. Okay, so for instance, over here, 38 is just has nothing specific about it. 37 is also on the Arduino connector pin 1. And is also connected to PA3. So over on here, and one of the things when you go and look at these are known as morpho connectors, which ST has more pins available because they are larger chips to pin your I/O out. These pink ones here are the Arduino connectors because there's a lot of shields designed for Arduinos and they wanted to be compatible with that. So they put that available. And so if I'm looking down, these are, of course, male connectors and these are female connectors. So then it depends also what kind of DuPont wires you have. Because, I need the one that has a male connector on one end and I'm plugging it into the breadboard. So you need a male-female connector. Or you might go to the Arduino connectors, in which case you need a male-male connector. So you have all that to contend with as well. So if I go and look at in Arduino world, if you used D15 for this chip, then that is also port B pin 8, which is also this pin 10 on this CN5 connector, and it's also pin 3 on this CN10 connector. So all of that kind of represents the same thing. Now, this is, again, Arduino world, and I will show you down the road firing up the Arduino and going and programming some stuff using that. There's a lot of libraries that have got things out there. So if I was looking at a part or that I wanted to interface, and they had a library in the Arduino world, maybe I'd fire up the Arduino world and use that. ST has a whole bunch of libraries that we can pull in and do things with, and they have a good graphical environment as well. And so I'm going to show you some of that during the first half of this course. When we go over to the ESP32s, we are going to be using the Arduino interface and using some of the libraries with that tool chain. So yeah, a lot of, by just looking at this, it looks like PB8 and 10 and 3 and 4 are all connected, but it is not, this whole side. And then you have to just count down to say, from the top of this is indicating where your ST link is. And so you make sure that's on the top, and then you just count down for where your pins are. If I was, again, on Arduino World and I referenced A0, it would know that that one is analog 0. If I am using my ST, it is port A bit 0. Yep.
Is it worth wiring this up like how we had the cyclone wired up, just for ease of access, or like how much would we use this in the course?
The one thing about ST's boards is it doesn't work really well on a breadboard, right? And so in the past, we used to use a chip called an STM32407, which is a taller discovery board, and it again is 2 rows. And so we actually built a breakout board to pull the pins out to so that you could take 2 breadboards together and stick it in and have access to all 100 pins. And so this is. We got these over the summer. They finally let us order stuff again. I have been working on putting something together for a board that would be possible for you to plug into and then just have access to your breadboard and things like that. And so that was, I did that over the summer. I would like a few more features on it to be able to put it out before giving you guys access to one, so I'm not sure I'll get it done in time for this go round, but we'll see. But yeah, because it can't plug into a breadboard, then you kind of have to just wire the wires out. But you do have access to the top and bottom of the wires, and for at least the first few labs, it's small. This is using another. This is acting as the Wi-Fi module, so we can connect to the network and push data to the cloud and do that kind of stuff. So there's a bit more wiring, in that part of it. So anyway, you need to reference this all the time and to see where to plug it in. Because when I go and look at the ST Discovery, it will say, oh, you're on PA0, but it may be over on the left-hand side, or you might see PC0 and it's down over here or up over here, and you have to look at what pin you need, go to this to see where physically it's on this Nucleo board. Okay? The next thing along the line, it's going to want me to download that one. Let me just go to... This is, I've grabbed all of these from the appropriate, lots of them from the ST site and things. But let me just have a look at this web. Where's my WebP? There it is there. So the next one on the list is this. And so what this has is... it's a block diagram of the features that are on board your 446. And so looking at that, and if you go to ST site and look up the 446, that is on their site saying, hey, here's the kind of things you expect. So I have a power system. You can use crystal oscillators on board this. We have a 32 kilohertz for timekeeping oscillator. That's on board. You can put a 4 to 26 megahertz oscillator on board. There's a footprint for it. It's not populated. The capacitors and the oscillator aren't there. So we use the internal oscillator. And we have an internal oscillator that has up to 16 meg. There are what's known as phase lock loops, and that allows me to take my 4 megahertz to, up to 26 megahertz external and turn it into 180 megahertz. So the oscillator's running at, could be running at 20 megahertz, for instance, and I can have the actual chip running at 180 megahertz. Okay. And so we have real-time clocks. So depending on the STM32F chip, you can have different real-time clock modules. And so the real-time module that this one has is will give you the days, minutes, leap years, all of that kind of thing. Some of the chips give you the number of seconds since January 1st, 1970. So you can store the date just as a big long number and then you parse it. This one will give you registers for seconds and minutes and hours. And one of the things about that last one that we looked at was there is a VBAT pin. So if I am running a clock and I hook up a coin cell to the VBAT pin, there's a couple of surface mount. There's a 0 ohm surface mount resistor you got to get out of there because VBAT is currently attached to your 3.3 volt supply. And so, but you can hook up coin cell and have battery backed up RAM, some of it, and have a real time clock. So I have some of these devices that I haven't used in a year or two, and then I will go and plug them in, and it's keeping time, and everything it was just happily in my drawer, running as just like your watch would or something like that. So that's the VBAT pin, and it's accessible. But if you hook a battery to it, you have to look at it's currently connected to the whole system, and that would drain the battery very quickly. You need to make sure that that is disconnected. Okay, but it gives you this real-time clock. It talks about a SysTick timer, and SysTick timer is a system-wide timer mainly for keeping track of, if you had an operating system or whatever, keeping track of the time. And it, by default, the system will set up the SysTick timer to give you a 1 millisecond tick. And so if I'm running at 180 megahertz or I'm running at 20 megahertz, it will give you the SysTick at 1 millisecond. So there's a bunch of macros there that look at the frequency and figure out what it needs to do to give you that 1 millisecond tick. Okay. There are watchdog timers, and so with watchdog timers, if I set those up, I have to keep feeding the watchdog or it'll hit a reset. So I have this as a pine beetle counter way up in the mountains, and a pine beetle will step on the button and it'll count 1, and that's awesome, but every 3 weeks it stops working for some reason, and I have to fly in a helicopter and hit reset, and then it counts more pine beetles. So that's by setting up a watchdog, if it fails to increment in your main loop and the timer overflows, it hits reset. Okay, it's a nice fail-safe. It's not an excuse for bad code, but it's a nice thing to have if you have something that really needs to run, and if it ever would get hung up, this is a way to prevent it. When you're debugging code and just writing it in the lab, you don't want that on because it's going to reset. You go, my screen keeps reflashing. Why is it? Because you haven't been feeding the watchdog, and so it overflows. So, but it's nice to have those features available. And then down here it says 50, 63, 81, 114 IOs. We can buy the 446 in all sorts of different configurations. How many ports do you need? And so sometimes it'll say, oh, you know, port H or something like that. Well, it might not be on your chip. And in fact, some of the other devices, some of the other peripherals might not be accessible to you because it needed to have a chip with larger I/O to be able to use some of it. So you have to bear that in mind with some of this. It has CRC, cyclic redundancy check. It has an ability to be able to prove that it's an ST part. And so some of the libraries and things that let you use, even in commercial products, they want you to only use them with ST parts. And this is a way of you being able to verify that it's an ST part. It also has a unique ID. You could put this into a product and have a unique serial number built in that you can go and access, so you know it's there's a subscription or whatever you want to do for it, that you can uniquely ID this device. We have some motor control PWMs. There are 10 16-bit timers and 2 32-bit timers. So there's a ton of timers. You could be keeping track of all sorts of things with this. Because it is an F4, you'll see M4 and F4, Cortex-M, Microsoft SD says, I have an STM32 F4. Well, it's based on the Cortex M4. And the difference between an M4 and an M3 is floating point and DSP instructions. So if you want to do some DSP, then you can use that in hardware. We'll talk a little bit more about this in the coming weeks, the nested vector interrupt controller. There is a separate piece of silicone that looks after interrupts. So I have a whole bunch of different peripherals, and I can say, okay, I want to set up, instead of having to keep holding a push button, I want it on an interrupt, and I want a timer on an interrupt, and I want a serial port on an interrupt, and I want all sorts. there can be a couple hundred different interrupts. And this nested vector interrupt controller will take all the different interrupt sources, see what's coming in, look at the priorities that you have set for the different interrupts, and tell the ARM CPU, this is the next interrupt that you handle. So it takes care of what's coming in and gives it to the processor to handle an interrupt. And it gives it what's known as a vector number. And it's very much like your CPU, your PC has a vector table. And so when an interrupt happens, it looks in the vector table for the address of where the interrupt service procedure is. I will talk more about it when we get to dealing with all of those kind of things. JTAG software debug in here is talking about your ST-Link interface. ST-Link talks to the JTAG interface, and it also has a software debug. It has the ability, when you are running code, for it to give out a back channel of silicone to give your variables, some of your variable information. This thing runs really fast and it could overwhelm a lot of serial interfaces and things, but you can say, I have temperature and humidity and all sorts of things, and when it's running its actual code, put that information out to another piece of monitoring software or your debug channels, and we will do some of that. Memory protection is they're trying to do things to prevent your code from, if it was proprietary code and you didn't want somebody stealing it, you can turn on memory protection. Somebody tries to access it, it usually erases itself and things. Your code is never secure. Somebody will always be able to defeat that. They'll probably buy the unit, destroy the unit, pay $1,000, and somebody will have the code for you, right? So, but it is another obstacle in the way. You know, Microsoft during when they were designing the Xbox and stuff, they did all sorts of things to protect the Xbox code. I think it was maybe a week, 10 days before a grad student at a university figured it out. And they did all sorts of stuff. Like they said, okay, let's have the CPU and let's have a fake flash chip, and it talked to the fake flash chip with garbage data, and we'll throw them off, and it's actually running code from an ASIC or like an FPGA. And so a grad student put a logic analyzer and was monitoring the data between the flash chip that was supposed to boot the system and was going, this makes no sense, and then moved it over and said, what's this other thing connected to, and looked at the FPGA and went, oh, well, that's starting to make more sense. And so, I don't know. Anyway, there's always a way around it is what I'm saying. Okay. 16-channel DMA, we'll talk about DMA. It's another piece of silicone that will allow your device to grab data from somewhere and move it somewhere else without the CPU being involved. Okay, so the CPU says, okay, we set up every time we get A to D values, we want to move it over to this memory location. Once you tell the DMA controller that you want that done, your CPU doesn't have to be involved with it anymore. It will just do it. And DMA controllers are used in hard drives, graphic cards, things like that to move large amounts of data without the CPU having to read and write the data from one place to another. So it can do things very, very quickly. Okay. As far as our connectivity, it says four lines of SPI. So a lot of devices that you go and talk to, accelerometers, gyros, temperature sensors, all sorts of things are connected with SPI, and so it gives you the ability to do a bunch of that. There is a camera interface. Again, some of these things I'd have to look at on the 64-pin chip. I'm not sure what all is available there. We'd have to go and look. It can talk 4 I2C channels, 2 CAN bus. So CAN bus is in any car from 2002. Is talking CAN bus among the automotive standard. USB 2 on the go, full speed and high speed. SD MMC, that's if you want to read an MMC card or SDIO card, you can go and read that. So 4U says 4 UARTs plus 2 LIN smart card IRDA. So you want to read smart card, put a smart card interface on it. It supports all that. IRDA. They used to have those on some laptops and things to be able to do IR communications and things. This can do that IRDA thing. So if your laptop can send that data out, we can also just put an IR interface and you can go and read just wireless remotes and stuff. That's a little different. IRDA is a specific protocol that's going between. Some of these, this one doesn't. We also have a serial audio interface. So if you want to get serial audio data and you're reading something in, convert it, spit it out to something, you could do that. You could use the DSP to change things with it. HDMI CDC, Consumer Electronics Control. So if you have, you want to have a remote and you talk to this device and have it plugged into HDMI, talking to your TV to change channels, do different things, this has the CEC interface, so you can have TV control if you want to do that kind of thing. And again, this is on this chip. Some chips don't have that module in there, so you look at maybe instead of a 446, you might look at a 476. They all will have different things. As far as our analog, we have here, it says 2 12-bit ADCs, 2 channel and up to 3 12-bit ADCs, up to 24 channels. There's also an onboard temperature sensor right on the die that's looking at the temperature of the die, not room temperature or anything else. So where I can use this is to say, I am in an enclosure out in the woods. It's the pine beetle counter again. It's going to step on the button and it's awesome. And so, but in the summer, if the sun's beaming down on the box, I can see how much my temperature is rising. Now, it's not compensated to be an accurate temperature. It can read up to 5 degrees, probably different from what it really is. And so one person's chip could read slightly different than another person's chip. But they will both read, if you read the baseline is this, and it goes up 5 degrees, they'll both go up 5 degrees. Okay? So it's accurate as far as the temperature differences, but the baseline isn't there. It's not being compensated at the factory for that. But it allows me to say, whatever I read as my normal working conditions, I'm getting too hot. And you could turn on a fan or do something like that. Okay? So we have those. As far as flash memory, the one that we have has 512K. So half a meg of flash. We have 128 KB of static RAM. We have space to be able to put external flash chips, external RAM and things on it as well. There's also a separate area that has a place, I said that you could have a coin cell on it, and there's a backup area of memory to be able to data log and keep it battery backed up when the power's out and things. So you can do things like that. The other thing that you can do with those kind of things is maybe I have things that I want to put in for when I calibrate something. So before going out the factory door, maybe you have a weigh scale and you want to zero it out before it gets packaged away and things. You could put it in that, or you could also write it to flash. It's something that doesn't happen too often. This is nice in that it can change all the time and it's battery backed up. There is a section for one-time programmable bytes. If that laser ID, the individual unique 96-bit ID is not good enough, you can also put something custom in there that you need. And so there's room for that. And again, we have our different SPI modules. So this is just kind of goes, does it have this thing? Does it do CEC? You can have a quick look at that and go, what are the kind of modules? Does it have I2C? Because I need to use I2C to hook something up. This gives you a bit of info on what kind of things are there. Okay. All of this, again, is in our week 1. So the next thing that I have there is a nucleo data brief. So the nucleo data brief, and so what I've done with any of these, I just went through, and so this is the name of the thing that was actually found, and I just put in, well, this is the the data brief for the Nucleo. So I just put this dash. This is the thing. If you were out searching it on the internet, you'd highlight that and go search for it, and that's where you'd find these things, mostly off ST site. What this does is it says, here are some STM32 Nucleo 64 boards. So I have the Nucleo 64. There's 144 pin chips as well. I have bigger, way more I/O and stuff in a Nucleo board. These are the little 64 boards. And so it says, okay, what kind of things? You also have a slightly smaller in the same form factor, which is a 48-pin device. It has one user LED, and it's shared on one of the Arduino pins. One user, one reset button. So we have a user blue button, B1 in what we had, and then there's the reset button as well. It has that 32768 oscillator for keeping the real-time clock going at an appropriate rate. Our board connectors, it says, is the Uno shield expansion, and then also the Morpho connectors. Now, you go and look at this, it's talking about the different boards, and it has a bunch of more information. And so it says, scrolling on down, the board reference, we have a Nucleo F446. So I'm going to look down here and see the Nucleo F446 this is the actual chip that's on there. This is it uses a mini USB, some use a micro, this one uses a micro. But the 446 and all of these ones over here, the board reference design is MB1136. So there's a schematic for MB1136. All of these different boards, the 303, the 334, the 401, all are based on that same schematic, all have that same footprint. That's the schematic, and here's the user manual. So depending on the board you get, you check this out, you go, I need that, and I need that. I downloaded those are in week 1. Okay, and so that's what I wanted to look at this for. What exactly is my schematic? What exactly is my board? Okay, and then that just goes essentially through that, talking about it. One other thing down at the end, when we say, okay, I'm an STM32 F446 and then RE. Well, R stands for 64 pins, and E stands for 512. So if I wanted something that had more memory, you might need an RG. Well, and there's those available, but they're not in this Nucleo small form factor. They're larger ones. Or you test everything out and say, I'd like more memory when I use the 446 for whatever I'm doing. And so you make sure you order an RG from DigiKey or something and get something with twice the flash. Okay, that's what all of those magical numbers mean. So I said, looking there, that the schematic was the MB1136. So you can actually search MB1136. There it is there. So I just put that in front. This is English MB1136 default schematic. And if you go look, it goes into exactly what's on your board. So if you need to see what's actually hooked up to a pin, where things are, there's the actual schematic for it. The other thing we looked at from that data brief was that the user's manual was 1724, UM 1724. Maybe I'll go over to this one. Where is it here? User manual 1724. Just so I don't have the whole ecology interface on it. Okay, so STM user manual 1734 based on the schematic MB1136. So when we go and look in here, it says, okay, getting started, about the ST link, how things are connected. There's a bunch of connectors on pins on board to be able to, with jumpers, and what all they kind of mean. And so let's see what it says here. So 3 LEDs, there's a USB communication LED, there's a power LED, and a user LED, and the user LED is LD2, and you guys have blinked the LD2 light on it, and again talks about some of the other stuff. The board by default we're plugged into is USB powered, and the USB is 5 volts, and then there's a low power regulator on board to be able to take it to the 3.3 volts. Arduino was 5 volts. The PIC you were running at 5 volts. We plug into USB at 5 volts, but our I/O is all 3.3 volt. Most pins are 5 volt tolerant. Most pins will go, okay, I didn't like you for doing that or whatever, but I'll tolerate that. But you definitely want to make sure that 5 volts doesn't get to, the power doesn't go on to anything but your 5 volt lines. So we're not trying to power up the chip from that. There are jumper positions, and there is connectors on the board where you could plug in 7 to 12 volts and have the regulator take it down to the 3.3 volts and do all that kind of stuff. The defaults that all your jumpers are on are fine, but there is a V-bus source, there's an external USB, and you would have to go look at the manual to say, okay, how exactly is all of this kind of stuff going? One of the things that you may have noticed is when you plug in this, it acts, for one, as the SD-Link. It will have a virtual COM port, and so you can talk serial data to it, and it by default brought out UART2 over to it. It also will be the debug port, and it also pops up, it looks like you've plugged in a USB stick, pops up as USB. So it will allow you to take a binary, a .bin file that you have got from somewhere, you plug it in, this USB stick comes up, and you drop in the bin file, and it will take that and reflash your system. Okay, so if you didn't have the ST stuff over, but you had the binary file, not the ELF file, but the binary file, and you dropped it in, it could flash your system with it. Okay. So that's nice. If you had something out in the field and you just gave somebody a binary file, they could plug this in, it would pop up looking like a drive, you could drag the file over and they've reflashed the system. So, and the reason it can do all of that is there is a bootloader in flash on the chip. So it comes there, and so we can, you can, even if you didn't have an ST-Link, you could program some of these. Okay, so that goes into some of the other information just like we had over there, but it goes into all the jumper positions, where the bootloader is, IDs, all of that kind of thing. This is kind of our picture, just saying, okay, you know, you have that snap connector part, there is where they could be separated if you wanted. And so if I put this in an end product and I didn't need the programmer, you don't have to be powering up or have another CPU hanging off there, you could snap it off. And we just have our reset black button, our B user 1 button. We have our different connectors. We have our LED, ours is LED2 on that connector. So there's where all of that is. It shows you in a little bit more detail. So if you're wondering, trying to find where some of this is, where some of this stuff has been helpful is, for instance, if you need to find, for instance, if I want the battery on board, I have to remove a 0 ohm resistor, and it will tell you in the document which one it is. You have to go find, you know, the shorting block 46, 52, 51. You have to find the one and get rid of the resistor if it says it doesn't want it connected. So you have to heat up a soldering iron and get rid of the resistor. Yeah.
There's an LD1 on the other side of the snap bar.
Yeah.
That's completely usable just as the LD2 is, right?
Where is the?
What is the USB interface?
Yeah.
Oh, yeah. This one is the ST-Link is notifying you that data is transferring down from the, and so when I'm debugging, you should see it flashing all the time. Okay. If you just go and program it and it's running by itself, you probably won't see it active. But if I'm debugging and there's communication going back and forth, that's when you're going to see that flashing of the storm. Yeah. But that's where you find out this kind of information about that. ST-Link. ST-Link is that programmer. You might see something, sometimes it talks in some data about a SWIM interface. That's to deal with some of their devices. The ST-Link can even, some versions of it will even talk SWIM. That's their 8-bit microcontrollers. We're using their 32-bit microcontrollers, so that is not to do with us as far as the connections and things. Okay. One of the jumpers on here on the ST-Link, for instance, is it? Nope, it's not that one. Back up a bit, I think. One of the jumpers, for instance, there's a right at the very top here. There's no jumper on it. That is telling the ST-Link to tell your PC that it wants 300 milliamps. Maybe you have a little bit more to drive. If you put a jumper on there, it tells ST-Link to tell the PC, don't give me any more than 100 milliamps. That's kind of what standard, if you don't ask for things, it's 100 milliamps. But they have it, so it's, we're hooking up a TFT screen and things that may have a little bit more. That's to tell it that it wants 300. Okay. So that's all documented in this document. The other thing that it shows in this document is that connector here. Again, this is a separate ARM chip and a separate debugger. And so if I pull these jumpers, I'm no longer talking to the chip down here. I can program something that I built, my own board that I built. So I can use that for that. All the documentation, is kind of in this kind of thing. And then it talks about all the different power supply options and things that we have available on there, and all the different jumpers and things. So if you want to find out about it, they also have JP6. JP6 is used to measure the microcontroller consumption. And so if where is my JP6 on here? So kind of right in the middle of the board. I've seen this happen before. If that jumper's off, there's no connection for any of the current to flow in your board. That's to measure how much current your ARM processor is taking. So I've seen people have it in their bag and then it gets knocked off or what have you. And so there's not a complete connection for the power. That's so that you can put an ammeter in the middle and measure what kind of current you're getting. Okay, and so it's powered on by default. If it's not on, you better have an ammeter or something in there because then you won't get things. This is just talking about the oscillators, and so there's the high-speed oscillator, and by default we are not connected up to the high-speed oscillator, so not used. And so if you put one on, there's some 0-ohm resistors you have to remove and things you have to do to configure it, and it's all outlined there. The 32 kilohertz supply, we do have that on there. It says the UART communication is connected up. The UART is available on PA2 and 3 of the ST microcontroller, and it can be connected up. And so, in other words, my UART is connected. So if I send something out in my program, it will go to the ST-Link. The ST-Link will put it through a virtual COM port, and I can see it on TerraTerm or something like that on the PC. And we'll talk a little bit more about that. And this just tells you about all the different solder bridges. The only one I'd like to kind of point out in here is I on one of mine put a battery because I have I put together a little game of Breakout and stuff, so I'll show you guys Breakout, and I wanted the high scores to be kept. So what do I need? I need to put it in backed up RAM, and so I needed a battery, and so I had to go here and say, okay, if I want the VBAT, just by default, there's a 0-ohm resistor, and so VBAT is connected to VDD. So it properly fires up and everything works, and my real-time clock works when it's powered off. But if I got rid of the 0-ohm resistor, then what I need to do is connect a coin cell, a 3-volt coin cell, to that pin to ground. Okay, and so then it's battery backed up. So I remove SB45. I look at the picture on the back of where SB45 is, and I get rid of that 0-ohm resistor. Yeah.
What exactly are you talking about with the 0-ohm resistor?
So on the back of the board, so they have multiple configurations. Where's the back? There's some on the front, but most of them on the back. So they say shorting blocks. So these are all 0 ohm resistors connecting this part of a wire to this part of a wire for some configuration. And so the default, they said you needed that. What did I say? SB45, right? So the documentation said SB45. So right here, can I zoom in on this? Let me zoom in on this. Control, thank you. Okay, so there's SB45. So the documentation said if I want to put a coin cell to battery back things up, I need to get rid of SB45. So on the front, when we look at that picture of where all my pins were, one of the pins is VBAT. I connect VBAT to the positive end of a coin cell, and the minus side of the coin cell goes over to ground. And this is just a 0 ohm resistor or just a wire, right? Just a jumper wire. Oftentimes in pick and place machines for automatic assembly, it's easy for them to put a 0 ohm resistor, which is a wire, but it's in the format that all the other resistors are in. And so you'll see it'll even say 0 on it. Some of these it just might be a blob of solder. And you just heat it up and get rid of it. Now if I didn't do that, my coin cell would be attached to the power of the whole rest of the system. And as soon as I power it up, my poor little coin cell is trying to power up my TFT display and everything else, and it will not last long at all. So when it powers up, it says, okay, use the power from your USB connector and the regulator to the 3.3 volts. When you power down, the 3.3 volt coin cell kicks in and only takes care of my real-time clock needs and my battery backed up RAM needs. That's it. Okay, so you can get years out of the coin cell sitting on one of these things. Okay, but this document tells you what these all are for. I may want an external crystal. I may want to hook up some external things, and you might have to move some of these around from their default design. So that's the part of this is here's a user manual talking about your Nucleo board, so you may need to look at that. So that's this UM1724. And again, I found that out because I went to the Nucleo data brief, and it told me what user manual was for my Nucleo board. So I was able to download the right one. And we also have the proper schematic if I wanted to get more in depth than just the look of where this SB45 is. Where is it in the schematic? You can go and find it. So you can go all the way down to that. So we're getting there. STM32 data sheet. So we've got this MB1 STM32 actual data sheet. So I want to go to look at the STM32F446. Oh, not block diagram. Data sheet. So the data sheet is, let me go to the start here. The data sheet says it is for the STM32F446, and it says it is 225 DMIPS, up to half mega flash, some RAM, all of this. And it talks about the core ARM architecture and a whole bunch of stuff we'll maybe talk about. Some of the stuff we already looked at in that block diagram, all of that kind of thing. The different sizes. If I want, it's a 10 mil by 10 mil pack for my little 64 pin. I can get a 144 pin chip, and it's 20 mil by 20 mil, but I got way more I/O. And so, you can do those. There's also insane fine ball grid array chips that you can get if you want them all in a really small space. So it talks about all of that. Now this is a 200-page document that goes over just some of the what's there and some of the electrical characteristics of the chip. There is also a much larger reference manual that goes in depth into things, but we'll start with this. We say, okay, it's got things like here talking about the actual ARM Cortex chip, real-time accelerator, the flash, clocks, all of that kind of thing. It's got a real-time clock, so I might find some information about that, about the timers and all this, and it gives you a little bit of information about all that. There is another document that we're going to look at that goes way in depth with all of this stuff, so I'll show you where some of that is coming up. The part of the data sheet I like to look at in this one is, I think, page 15, so let me just get to page 15. I think it's on page 15. Page 16. Okay. This is what I like to refer to when we start kind of visualizing what's going on in your chip. This is inside the black piece of plastic. This is in there. This is inside this. And in a very small corner is the ARM chip up in the corner. That block right there is your ARM Cortex chip inside that black piece of silicone. It has a whole bunch of other stuff. Look at your ports down there. Where did we flash the light on? I can't even remember. Port B, right?
B.
So port B is here. Here's port B. So it goes here, and it goes to this advanced high-speed bus that's 180 megahertz, which talks to this advanced high-speed bus matrix, which then goes up, and there's an instruction bus, a data bus, and a system bus that the ARM Cortex talks to. The data has to get clocked in or out of here and get onto this bus and get onto here and go into your ARM chip. And that's where I said it's turning on the clocks for all those buses. You used to have to do that. You used to have to look at this and go, oh, I'm on this bus, and then I'm on this bus, and turn all of those on. It does it. It automatically, nicely does all of that stuff for you, and maybe more than you want, kind of thing. If I'm over here, I'm on the advanced high-speed bus 1 there. What's this one down here? Let me just scroll down a little bit here. Oh, if I want to use UART4, I'm on the advanced peripheral bus. I can run at 45 megahertz. It goes to the advanced peripheral bus over to the advanced high-speed bus, and then over to the ARM chip. All of those can be turned off and save power, or turned on. It's doing all of this for you. When you say, I want to go and I want to use UART4, it turns all of those on, gives you the initialization code. This is what I'm going to start to refer to find out what it is and where I need to go. It doesn't matter as much as it used to. You used to have to look at it and trace the path and make sure everything was on along the path. Okay? But that's what the data sheet is. It's got lots more useful stuff. We'll talk more about it next day. Thank you.
ML, you buying stocks in ARM? I think you're going public.
Yeah, they're going public.